Hey everyone, and welcome back to the channel. Imagine a cosmic lightning bolt, but not one that flashes across a stormy sky here on Earth. Imagine a burst of energy, billions of times more powerful than our sun, blazing across the universe from billions of light years away. It lasts for mere milliseconds, a blink-and-you-miss-it phenomenon, yet it carries enough energy to reshape our understanding of the cosmos. These aren't hypothetical fictions from a sci-fi novel. These are fast radio bursts, or FRBs. They are real, they are happening. And for over a decade, they have been one of the most profound and perplexing cosmic glitches ever detected. A sudden, violent, inexplicable shriek from the depths of space that leaves scientists scrambling, asking the fundamental question: why? Why do they appear? What power unleashes such a cataclysmic flash? And what cosmic secret are they trying to tell us about the universe we thought we knew? Our story begins in 2007, not with a live detection, but with a retrospective glance into archival data. Dr. Duncan Lorimer and his team were sifting through observations made 6 years earlier by the Parkes Observatory in Australia. They were searching for pulsars, rapidly rotating neutron stars that emit beams of radio waves. Instead, nestled within a 3-year-old dataset, they found something entirely new. A burst of radio waves so intense, so brief, and so utterly unlike anything seen before that it initially defied explanation. This event, later dubbed FRB 10621, after the date it was observed, was a singular, powerful spike that lasted less than 5 milliseconds. Its most striking feature, however, was its dispersion measure. To understand dispersion measure, imagine a light beam traveling through water. Different colors or wavelengths travel at slightly different speeds. The same principle applies to radio waves traveling through the vast cosmic ocean of ionized gas, essentially, free electrons and protons floating in space. Higher frequency radio waves travel faster through this plasma than lower frequency waves. So when a broadband radio signal from a distant source reaches us, the lower frequencies arrive slightly later than the higher frequencies, creating a characteristic smear or chirp in the signal. The amount of this smearing, the dispersion measure, tells us how much interstellar and intergalactic plasma the signal has passed through. And for FRB 10621, that number was enormous, far too large to have originated from within our own Milky Way galaxy. It had to be extragalactic, traveling for billions of years, crossing unimaginable distances to reach us. This initial discovery was met with a mix of excitement and skepticism. Was it a glitch in the telescope? Terrestrial interference? One-off anomaly? For years, FRB 10621 remained an isolated incident, a ghost in the machine. But then, in 2011, another FRB was detected, and another, and another. By 2014, enough had been found to confirm their reality. These weren't instrument errors. They were real, powerful, and incredibly mysterious phenomena emanating from the far reaches of the universe. Each new detection only deepened the enigma. They were characterized by extreme luminosity, often outshining entire galaxies for the briefest moment, and by their incredible brevity, always lasting mere milliseconds. Their extragalactic origins were undeniable, pushing the sources of these bursts billions of light years away, some even hinting at origins from the very early universe. The sheer power required for a signal to be detectable across such cosmic gulfs immediately suggested truly cataclysmic events. Early theories for these non-repeating FRBs focused on singular, destructive events. One of the most compelling was the idea of colliding neutron stars. Neutron stars are the superdense remnants of massive stars that have gone supernova, packing more mass than our sun into a sphere only about 20 kilometers across. And two of these incredibly dense objects orbit each other and finally merge. They are known to produce gravitational waves, gamma-ray bursts, and potentially a powerful electromagnetic pulse as their magnetic fields interact and new, even more exotic objects like hypermassive neutron stars or black holes are formed. Such an event would certainly generate enough energy for an FRB. Another possibility involved the collision of a neutron star with a black hole, or perhaps the collapse of a supermassive star directly into a black hole, an event sometimes referred to as a collapsar, which can also power energetic outflows. Even the idea of a rapidly spinning, young neutron star collapsing or undergoing a massive starquake was considered. All of these scenarios had one thing in common. They were one-off, terminal events that would utterly destroy or transform the progenitor object, thus explaining why these FRBs never seemed to repeat. But then the universe threw us a curveball, a truly cosmic glitch that shattered the neat separation of theories. In 2016, astronomers using the Arecibo Observatory in Puerto Rico, before its tragic collapse, announced a groundbreaking discovery, FRB 121102. This burst, first detected in 2012, wasn't a one-off. It repeated. Not in a predictable pattern, not like a lighthouse beacon, but in seemingly random, sporadic flashes from the exact same point in the sky. This changed everything. If FRBs could repeat, then their source could not be a catastrophic, self-destructive event like a neutron star merger. The progenitor had to survive the burst, meaning a continuous, albeit intermittent, engine was at play. The existence of repeating FRBs instantly ruled out many of the leading theories for the non-repeating variety and opened up a whole new Pandora's box of possibilities. What kind of object could survive such an immense energy output and do it again and again? The hunt was on to localize FRB 121102 to pinpoint its exact cosmic address. This monumental task was achieved in 2017 using a network of radio television